Good afternoon, Hoylake and West Kirby. This is a rather tongue-in-cheek stocking filler for the festive season. I'm going to be talking about the question whether Santa is compatible with the laws of physics, or if you prefer, how many laws of physics does Santa actually break? So we know that Santa is, well, allegedly, a portly, jolly fellow with a white beard and a penchant for wearing red suits. But just because he has questionable fashion sense, that doesn't mean he cannot exist. So what about the claims that are made for Santa at this time of year? We're looking at the statement that he visits all households on Christmas Eve to deliver presents to all qualifying children. And qualifying in this context means whether they're on the naughty or nice list. Can we reconcile these feats, these alleged feats, with our understanding of science? And in particular, I thought it might be interesting to use the science that's been described in some of my other talks to see whether any of those other talks can help us understand whether or not it's reasonable that we think of Santa either being compatible with or breaking the laws of physics. So I'm going to cherry pick a few little bits and pieces from other talks I've given. Here's a smattering of them, about half the talks that I give that are basically science-based. So let's actually look at the statement we are dealing with. This is the statement we are going to unpick. Santa visits households on Christmas Eve to deliver presents to children. And we're going to unpick that one word at a time and see which aspects of this statement don't make any sense. So firstly, let's think about how many children are involved. So the Earth's population is about 8 billion. 25% of the population are children, and let's assume that half of them are eligible for Christmas presents. In other words, let's assume that Santa is fairly generous and quite charitable and will deliver presents to children even though perhaps they're not in Christian families. So that means about 1 billion children get presents. And here I'm making the rather radical assumption that there's nobody on the naughty list and they're all on the nice list. Any parents amongst you or grandparents may question that particular assumption, but that's what we're going with. So we're dealing with 1 billion children. Okay, so Santa allegedly visits lots of households. So how does he get around? What's his mode of transport? Well, it's a sleigh pulled by flying reindeer. But can reindeer fly? Well, insects fly. And birds fly, and pterosaurs fly, though you don't see many of them these days. And of course, some mammals can fly. But if reindeers can fly, they choose not to do so for a lot of the time, because we have very little evidence of any flying reindeer. But remember, in science, absence of evidence is not evidence of absence. So just because we haven't got any photographs of reindeer that are in the process of flying, it doesn't mean they can't. So we must say that the jury is out on that one. So how fast would Santa have to go to make his deliveries? Well, to visit 1 billion children in one night, let's assume the night is approximately 36 hours. It's not just 12 hours of darkness because A, we're in winter, but on a global stage, it's not really a question of winter or summer because, of course, we've got northern and southern hemispheres. If Santa uses the time zone sensibly, then he has approximately 36 hours to do his visitations. So if he visits 1 billion children in 36 hours, he would have to travel at something like 2,000 kilometers per second. But that is less than 1% of the speed of light. And we know from previous talks, and we know from our understanding of the universe, that the speed of light is an absolute speed limit, and therefore if Santa is only going at 1%, or perhaps a little more if he wants to spend some time at each location, if he's only travelling at a few percent of the speed of light, then he's not breaking any laws of physics. So we know that no objects can travel through space faster than light can travel in a vacuum. Space itself, we know that we live in an expanding universe, and space itself can expand faster than the speed of light, but that's different. Here we're talking about objects moving through space. So no laws broken up to this point. Okay, but surely if he's moving really fast, wouldn't the sleigh get really hot? Wouldn't we have roast reindeer? Just as a meteor or an asteroid entering the Earth's atmosphere would heat up, and there's a common myth that things going fast heat up because of friction. It's not actually friction, it's because an object moving through the Earth's atmosphere would compress the air in front of the object, and that compressed air would heat up. That's because compression produces heat. That's part of what I call the ABC of stellar evolution, where we try and understand how stars evolve and why they evolve the way they do. The C of the ABC stands for compression produces heat. So if you compress gas to make a star, the star gets hot. So presumably the same would be true of a sleigh travelling very quickly through the Earth's atmosphere. The air in front of the sleigh would get compressed and would heat up. Even if the sleigh was aerodynamic, that would still be a problem. Surely it would still be compressing air to the point where the whole thing, sleigh and Santa and reindeer, would be glowing white hot. So how do we get around that problem? Well, if compression produces heat and hot objects radiate light, or at least the ones we are aware of, you take a brick and you heat it up, it starts to get red hot and eventually gets white hot. So shouldn't that mean that Santa and the sleigh should be easily visible? Well, maybe they were. But it's a bit of a stretch to say that actually Santa and his sleigh were responsible for the Star of Bethlehem. The timing, of course, doesn't work out too well. But you could argue that if Santa and his sleigh are visible as a bright light in the sky, well, plenty of people claim to have seen bright lights in the sky. So maybe that's not so surprising either. But there's a much better explanation as to why we wouldn't necessarily expect Santa and the sleigh and the reindeer to glow white hot. Because all we need to do is to think about, well, is there any material that we know of, what do we know of, that does not emit or indeed reflect light of any type, any wavelength, any electromagnetic waves whatsoever? There is a material that will not glow white hot, no matter how hot it gets. And that's dark matter, which does not emit light. So maybe Santa and his sleigh are made of dark matter, and that's why we don't see them glowing white hot when they travel really fast through the Earth's atmosphere. It also explains, of course, why the sleigh doesn't show up on radar, because it doesn't reflect radar, which is just another electromagnetic wave, microwave radiation. Okay, so that's a possibility. Let's have a look at the next element of this statement, that Santa visits households. Okay, let's go with the chimneys first. How can Santa get down so many chimneys so quickly? If he's visiting all of these places and he's visiting 1 billion children, he would have to squeeze down something like 3,000 chimneys a second. Now, we've just said that Santa is a rather portly fellow, and so surely he will not be able to squeeze down that many chimneys in a second. So what are the alternatives? Well, if we use what we know about the way the world is made up, the world is, and everything in it is made of atoms, and atoms are made of nuclei and electrons orbiting around them. But if we were to replace the electrons with muons, muons are a sort of heavier cousin of the electrons. They have a lot of the same properties, but they are 200 times more massive. If we were to replace the electrons with muons and make a whole set of new atoms, all of these atoms would be something like 200 times smaller. Which means if Santa is made of these atoms and we replace the electrons with muons, then Santa, instead of being a little less than 2 meters tall, would only be about 1 centimeter tall, 200 times shorter and 200 times slimmer, which means he would go down a chimney no problem whatsoever. So I don't know how Santa would replace all of his electrons with muons, but there's nothing in the laws of physics that says you can't. So maybe that's what he does. That doesn't help if the house or the apartment doesn't have a chimney in the first place. So regardless of the fact he could be quite small, if he hasn't got a chimney to go down, how can Santa get inside a house with a locked door and all the windows closed? Again, we can use our knowledge of subatomic physics and the quantum world, which tells us that you can get from outside an object like a locked room to an inside, even though the doors are shut and the windows are shut and there's solid walls. According to quantum theory, it is possible to go from the outside to the inside. It's called quantum tunneling, and it means going through a wall, even though Isaac Newton says it should be impossible. It is impossible to go through a solid object, says Isaac Newton. Quantum mechanics says, oh no, it is possible. So if it's possible for quantum-sized objects like atoms and molecules to behave this way, if Santa is made of atoms and molecules, well, why can't he behave that way as well? So quantum mechanics does allow Santa to gain entry to as many houses as he wishes without having to have an open door or an open window or indeed a chimney. Okay, what have we done? We've done children and visits and households. It is stated that he can do all this on Christmas Eve. Okay, all in one night. How can Santa make so many deliveries all in one night? Even if he's travelling at relativistic speeds between each delivery, how can it all be done in 36 hours? Well, according to our knowledge of quantum theory, again comes to our rescue. We know that subatomic particles can be in two places at one time. So if atoms and molecules can be in two places at one time, and again, Santa is made of atoms and molecules, why can't Santa be in two places at one time? And if that's allowed by the laws of physics, why can't he be in three places at one time? Or 4, or 17, or 10,000? So yes, he's got to make a lot of deliveries, but maybe he's allowed to be in more than one place at one time. And if you really don't like the idea of Santa being in more than one place at a time, then there are alternative ways of getting around this problem of visiting all of these places in 36 hours. And that is that in principle, he can distort space and time. We know that matter can distort space and time. We know that, for instance, close to neutron stars and close to black holes, space is very distorted. Maybe Santa has figured out a way of distorting space such that instead of Santa having to visit all of these houses, maybe he's figured out a way of distorting space in such a way that all the houses come to him, rather than him having to visit all the houses. I'm not sure how he would do that, but again, this is perfectly compatible with our understanding of the laws of physics. So we've had children and visits and households and Christmas Eve. What about delivering presents? Well, Santa's sack, wouldn't that have to be huge? How could Santa carry all the presents for the children we're talking about? One present, let's assume one present for each of the 1 billion children we're talking about. How could the sleigh possibly hold that many presents? Let's assume that they are not huge presents the size of a full-size teddy bear. Let's assume they're relatively small, but still, if there are 1 billion of them, how could the sleigh hold that many presents? Well, again, it is possible that the sleigh is bigger on the inside than it is on the outside. And no, I'm not talking about science fiction such as Doctor Who's TARDIS. We know, for instance, that black holes are bigger on the inside than they are on the outside. So if it's possible for a physical object to be bigger on the inside than the outside, then why can't the sleigh be bigger on the inside than the outside? So again, that doesn't disobey any particular laws of physics that we understand. And again, if you don't like the idea of a sleigh that's bigger on the inside than the outside, there is an alternative way that Santa might be able to achieve this. We think of the universe as being made of 3 space dimensions: forwards, backwards, left, right, and up, down. But many people believe that the universe actually has more than just 3 dimensions of space. And maybe there are. Maybe Santa has figured out a way of moving the presents all into one of these other dimensions, and then he visits the households, and one by one he picks the presents out of this other dimension and brings them back into our 3 space dimensions in order to put them under the tree. We don't know how many dimensions there are. We can only perceive of 3 of them. There might be a lot more. Maybe Santa has figured out a way of accessing these other dimensions. Yes, you might say, that might be possible. But wouldn't it need a huge amount of energy for Santa to do all of this, whether it's moving really fast or carrying lots of presents or distorting space and time in order to allow the deliveries to be made? Surely it would be a huge amount of energy. Santa and his sleigh and 1 billion presents moving at possibly relativistic speeds. Yes, indeed, it would need a huge amount of energy. Where could that energy possibly come from? Well, we're back to one of our staples. Why can't it be powered by a black hole? If a black hole could power a starship and send it to the stars at huge speeds, why can't a black hole be used to power a sleigh? A sleigh is altogether a smaller mass than a starship. So why can't you use a black hole to power a sleigh? That would give you a huge amount of energy to play with. Again, there's an alternative. There's a rather important alternative and an energy source that so far we've been overlooking. What is the elephant in the room? The elephant in the room is, what happens to all the mince pies? Now, we don't know how many mince pies are set out, but if Santa could convert the mass of all the mince pies that are left out for him, then that would give him a huge amount of energy to play with. We know the conversion rate between mass and energy equals mc squared. So if we know the mass of all the mince pies that he's given over the night of Christmas Eve, then we can work out how much energy he has available. So let's do the maths. Sorry if you don't like maths, you can look away now if you're of a nervous disposition. One mince pie has a mass of about 50 grams. If we multiply 50 grams by the speed of light squared, we get the energy in one mince pie. It's about 5 times 10 to the 15 joules. I'm using joules, not calories, because that's the energy unit preferred by physicists. I'll explain how big a joule is in just a moment. How many mince pies? Well, let's assume that not everybody puts mince pies out for Santa. Let's assume it's just a few % of households leave a mince pie for Santa. Let's say 20 million, because it makes the numbers easier. 20 million mince pies, that means 20 million times the number I've just calculated. That gives us a total energy available to Santa over the night of 10 to the power 23 joules. How much is 10 to the 23 joules? Physicists understand these units, nobody else does, so what do we mean by that many joules? Well, it's the same amount of energy as a nuclear power station running for 1 million years. So you could say that that amount of energy is roughly equivalent to, during the night, Santa has access to the equivalent power output of 1 billion nuclear power stations, something like that. An absolutely huge amount of energy in the mince pies. Okay, how do you get that energy out? Saying that that energy is there is one thing, but how do you extract energy from a mince pie? Well, there's at least 2 options I can think of. One is you take the mince pie and you take an anti-mince pie and you collide them together in the Large Mince Pie Collider at CERN. So matter and antimatter release energy, but then you have the problem, well, yes, that would release a huge amount of energy, but where do you get the antimatter equivalent of the mince pies from? That's a little bit of a problem. So that doesn't work so well. But there is an alternative way of extracting energy from a mince pie. You can't necessarily extract all of the energy from a mince pie in this way, but you can extract a reasonable fraction of E equals mc squared from a mince pie if you drop it into a black hole. Now, you might think that dropping matter into a black hole, the matter is just lost forever. But actually, in the process of matter falling into a black hole, generally speaking, the matter gets quite hot and can release a huge amount of energy. Our sun, for instance, is not very efficient at converting matter into energy, less than 1% efficiency. But if you drop matter into a black hole, you might get 10% or 20% or more of that energy back from dropping the matter into a black hole. We know it's a very efficient process because, for instance, that we know that there are black holes called quasars where the matter is falling in and being converted into radiation. Now, the matter that's falling into these quasars is probably not mince pies. The matter there is probably gas and dust and probably stars that are falling into the black hole, and in the process, the matter is being converted into radiation. It is such an efficient process that these quasars can be seen even on the other side of the observable universe. For instance, in 2020, I actually tried imaging one of these quasars even without using a telescope. This is with my Nikon camera. I took an image of one of these quasars that is 25 billion light years away, and it's possible to pick up the light from this quasar even without a telescope. That shows you just how much energy you can get out if you put enough matter into a black hole. So maybe that's how it's done. Now, how much energy could you realistically get out of dropping mince pies into a black hole? Surprisingly enough, I can't find any research papers on this topic. I can't find anybody who's published exactly how much you can expect, but I think it would be a large fraction of the total energy available that we calculated just a moment ago, the equivalent of a nuclear power station running for 1 million years. So more than enough energy if Santa can access that energy to do all of these incredible things. How could Santa actually do all that? Even if these things are allowed, how can Santa actually, for instance, manipulate space and time? Well, one thing we're forgetting is who says Santa has to be human? No one's seen Santa because, of course, all children are asleep when Santa actually arrives to deliver the presents. So we don't actually know what Santa looks like, despite the various caricatures that we have in Christmas cards and on TV, etc. So we come back to the original question. How many laws of physics does Santa actually break? Well, as you can gather from what I've been saying, I think the actual answer is none. So feel free to draw your own conclusions about the existence or otherwise of the portly, jolly fellow with a white beard and a penchant for wearing red suits. And regardless of your conclusion, I'd like to wish you all a very Merry Christmas.
Same to you.
Thank you all for listening.
Good. Thank you very much indeed. That's great.